So I'm going to talk about, some of what I'm going to talk about is joint work with Benindia Day and Elchanan Mazel. Some of it's just with Elchanan. Okay, so in this week we're supposed to talk about functional inequalities on discrete spaces, but I want to start by talking about functional inequalities on Gaussian space. And I apologize to people who were here for the last workshop because I have to repeat a reasonable amount of what Elchanan and I said, but I think there's enough people who weren't here. So, okay, so I want to start out by considering two Gaussian random variables. Each one is in Rn, and so the joint distribution is in R2n, mean 0, and each one by itself is standard Gaussian, but they have some correlation between them, right? And there's a very beautiful theorem. Okay, so what I want to do is I want to ask, given some event, can it be that there's a very good probability of both x and y landing in the event? Okay, and there's a very nice theorem about this, which is due to Christa Burrell in the 80s. Which says that this probability is maximized if I take A to be a half space. And I can even make it a little bit stronger, so I give you two events. And I want to ask you to maximize the probability that x is in one event and y is in the other. And this is still maximized by half spaces, and not only that, but the half spaces should be parallel. So the theorem says that for all A and B, this probability is bounded by some other probability, the probability that x1 is smaller than phi inverse of the measure of A, and y1 is smaller than phi inverse of the measure of B. And here phi is the Gaussian CDF function. And so you'll see here that what I've written here on the right is the probability that x is in some event, which is a half space of measure, the same measure as A, and this is the event that y is in some half space with the same measure as B. And so what this inequality is really saying is that this probability is maximized for parallel half spaces. Okay? All right, so this is an inequality about sets, but we should be talking about functional inequalities. Yeah, rho is positive, thanks. You can talk about rho being negative too, and then everything that I say will also work for negative rho, except that inequalities will reverse. So, all right. So here's a functional version. Which is equivalent to the original version. And so what I do is I define J as a function from the square to, well, I guess it maps into 0, 1. And there's a parameter rho, which I'll sometimes suppress. But J of A, B, and rho is the probability that x1 is smaller than phi inverse of A, and y1 is smaller than phi inverse of B. Right, and sort of rho is implicit in the joint distribution here, right? So the way I've defined J is it's the noise sensitivity of two parallel half spaces with these volumes. And then the point of making this definition is now I can sort of write this theorem in a way that looks maybe a little bit nicer. So for all f and g, mapping from Rn to 0, 1, the expectation of J f of x, g of y, is smaller than J of the expectations. Okay? So of course, it's pretty easy to see how this one implies the original. Right? What I do is I set f and g to be indicator functions. And then if I set f and g to be indicator functions, then the point is that you can easily see that J of 0, 0 is the same as J of 1, 0 and J of 0, 1. Those are all 0. And on the other hand, J of 1, 1 is 1. So when I plug in indicator functions here, this thing on the left-hand side is just the indicator that they both land in the set. right? And so this left-hand side here is the same as the left-hand side here, and j was just defined so that the right-hand sides are the same. Okay, so the functional inequality implies the set one, and you can actually go the other way around too, but I think maybe I won't say that today, so they're actually equivalent. Okay, so the broad thing that I want to talk about is quite vague, I guess, but let me write it like this. So I want to ask for which joint distributions and for which functions do I have an inequality like this? Okay, so some things are very easy, right? So if I take distributions where x and y are independent, then this is always going to hold, right? So really the question is, for which distributions with non-trivial dependence between x and y does an inequality like this hold, right? So I'm trying to ask for distributions where there's dependence, but you can't find events that are very correlated. Okay, so here's a definition that measures the dependence of two variables. X and y have Runny correlation rho if for all functions f and g, the covariance of f of x and g of y is smaller than rho times the square root of the product of the variances.
So J is concave.
J is not concave. If J were concave, then this would follow from Jensen's inequality.
Individually.
If J was concave jointly in both, in each variable individually, J is concave. Yes.
So that's what you use to get the...
Okay, so I'll tell you what's very important about J. It's going to come up later. So I write J xx for the double derivative of J in the first variable, right? And then I can look at the Hessian. Right, so concave would be that, right? But it actually satisfies this. Okay. So Michel Ledoux proposed the name rho concave for such functions. And in fact, when I have Gaussian variables, this inequality is true for every rho concave function. That's sort of the crucial property. Okay, so here is some measure of dependence, right? I say the things have correlation rho if they satisfy something that's stronger than Cauchy-Schwarz, because I can put a rho on the right-hand side. Okay, and you could ask, do things that have L2, any functions. So, I mean, you'll notice that, yeah, okay, any functions.
J is a function coming from the Gaussian, or is a function coming from the law of x and y?
Let's say the Gaussian. Okay.
So it's a fixed G.
I fix the function j, and I ask this question for this function j, right? Okay, so the first question is, does Runny correlation rho imply star? And the answer is clearly not, because... So what if I take x and y to be Bernoulli with correlation rho? Right, so that means... So it's pretty easy to check that Bernoulli variables with correlation rho also have Runny correlation rho. And the reason is that there are sort of no non-trivial functions to test for, because this equation is affine invariant, and so there's nothing to check. Right? Okay, and then for Bernoullis with correlation rho, I can take my event A to be the event that x is 1, and my event B to be the event that y is 1. And then I have probability that x equals 1, y equals 1 is 1 plus rho over 4. Okay, and now, well, if I plug in, on the other hand, j of these probabilities, right? Each of these events is probability a half. This thing turns out to be 1/4 plus, I think, if I try and do it by memory, I'll get it wrong. One-fourth plus 1 over 2 pi arc sine of rho. So this is what you get for j of a half, and you can test it because what's j of a half? It's the, you can write it as the integral over R2, the Gaussian measure, against a wedge. And then the question is just what's the angle of the wedge. So that explains that. And now the point is that arc sine is a concave function on the interval 0 to 1. And so this is always smaller than that. OK, so the answer is Runny correlation rho does not imply this. OK, on the other hand, you can see that if I have two variables with Runny correlation rho, then this is clearly the maximum correlation you can get between events. Right? And that's just because if you plug in the two events into this, then that's what you get. Okay? And so I guess one thing that you can see from this is that in some sense, Gaussians with correlation rho are less noise stable than Bernoullis with correlation rho. All right.
Can you explain the last sentence?
So half spaces are the most noise stable sets for Gaussians. And their noise stability is strictly smaller than the best noise stable sets for Bernoullis. Right? This is, let's consider just sets of measure a half. Right? This is the best noise stability I can get for two Gaussian sets of measure a half. And
You didn't define what noise stability was.
Yeah.
So I wasn't in last week's list.
Sorry. I define this thing to be the noise stability of a set. The probability that two correlated things fall in it. Okay, so, and I guess what I'm hoping is the main message of the talk is that rho correlation does not imply that your noise stability is less than Gaussian, but rho correlation plus lots of small effects does. And this is a very vague statement because, unfortunately, what we know so far is pretty vague too. But anyway, let me give an example. And this example is the famous majority of Stablest theorem, which is due to Mossel, O'Donnell, and Oleskiewicz. And it goes like this. So now I'm going to move from Gaussian space to discrete space. So I consider the cube, plus minus 1 to the n. And I take x to be a uniformly random element of this space. And y, well, so I define yi by, for each bit, I set yi to equal xi with probability xi with probability rho, and with probability 1 minus rho, I take an independent random sample. Right? And so now what this means is that for every bit has correlation rho between x and y. Right? And they're independent. Okay, and so now the theorem says this, that I look at this function, I look at this equation star, and I want this to hold for the cube. And of course, it's not true because of this example, right? This example, I can just look at functions of the first bit and it won't be true, but it's true if I add an error term to the right-hand side. And the error term depends on the influences. Right? So I don't really want to define influences if you don't know what they are, but basically, if f and g don't depend on any one bit too much, then this inequality is true. Okay, so this is one example of something that answers my question. Right? So the example is, if I have row correlated vectors on the discrete cube and functions which don't depend much on any one coordinate, then it satisfies the Gaussian noise stability bound. Okay, now I want to give you a proof of this. And this proof is, it's not the original proof, but it's a proof that was joint work with India and Elkanon. And the way the proof is going to work is I'm going to prove a two-point inequality and then tensorize. Okay, so I want to prove a two-point inequality. So let n equals 1. Okay, I want to consider this. I'm going to Taylor expand it around the expectation of f and the expectation of g. So there's a first order term. Right, so it's right, it's the difference in the first variable times the first derivative of the point that I'm Taylor expanding around, and then
You also have J8 expectations, right?
sorry?
You know J8
Ah.
expectations.
Yeah, that's true. Okay, thank you. Okay, and then this is the first order difference. Okay, and now I get a second order term. And the second order term is a quadratic form. I'm going to start writing f tilde and g tilde for f minus the expectation. And then what I have here is the Hessian of j, f tilde and g tilde. Okay, and now there's a third order term, and now I'm going to give up and just say order of f tilde cubed. Okay, so now I'm going to take expectation of both sides, and what happens when I take expectation of both sides is that the first order terms vanish. And let's see what happens to the second order term. So expectation of j fg is equal to j of the expectations plus the second order term. And the second order term, when I multiply this out, is a half. And then what I have in the matrix is the variance of f times jxx. On the bottom I have the variance of g times jyy. And here I have the covariance on the diagonals. And then there's a third order error term. Okay? So I haven't done anything complicated now. Okay, so now if you look at this matrix, okay, well, I told you up there that this matrix with the rows is negative definite, right? So there's, so basically what I want to do is I'm going to apply the Runny correlation definition there to replace this covariance by rho times the product of the square roots of the variance. And then this condition here on the Hessian being negative will tell me that the second order term is actually non-positive. All right, so you put that all together, and I claim that I've showed this is smaller than j of the expectations plus something which is of order of a third order. So that's the base case of the induction. There's almost nothing there. It's just a Taylor expansion and then a bound on the second order term. Okay. So now I want to do the inductive step. And actually, I claim that the inductive step is almost trivial. So let me just cheat a little bit, and I'm going to prove the inductive step without the error term. OK, so I suppose, and this is unfortunately not true, that the expectation of j of f of x, g of y, is smaller than j of the expectations for x having n minus 1 variables and y having n minus 1 variables. Okay, and now I'm going to do it for n variables. Right? So expectation of j, so now f is a function of x and xn, and g is a function of y and yn. And this expectation is the same as if I take the expectation of the conditional expectation, right? And now the point is that conditioned on xn, this thing is actually only a function of n minus 1 variables, right? So I apply the inductive step conditionally, and I get j of, and in here is expectation of f given xn, expectation of g given yn.
Do you want a condition on both x and y?
Well, yeah, OK. So I can put an xn and yn here, but in fact, it doesn't matter because all of the other x's are independent from yn. Right, so. OK, and now what I have in here is something of the same form, but now what's inside are both functions of one variable. And so I apply the base case of the induction, and I get this is smaller than j of the expectations. OK, so this was the cheating version where I didn't use the error term, but now if you want to do the induction with the error term, you just do exactly the same thing, but now you have to keep track of what happens to the error term when you do the induction, right? And I think I might leave that bit out unless someone really wants to see it. I'll just tell you what happens at the end. What you actually get is expectation of j of f and g is smaller than what you wanted, plus an error term, which looks like the sum of some martingale differences cubed. So where in here fi is the expectation of f given x1 to xi. So that's what you get if you follow through the induction and keep track of what happens to the error terms. And you'll notice that there's a cube here on these martingale differences, and that's actually quite important. OK. OK, so actually let me, I'm going to call this a theorem. Okay. This is something that's true for any functions f and g on the cube, that you have this sort of Gaussian noise sensitivity bound with an error term. OK, and now two remarks. So it turns out that from this sort of general statement, you can deduce both the majority of Stablest theorem, and you can actually deduce the Borel's theorem for Gaussians. Well, actually, so the majority of Stablest theorem implies Borel's theorem. So that's a little bit redundant what I just said, but to get from here to Borel's theorem is actually very easy. And you don't actually have to go through majority of Stablest. So let me show that first. OK, so I consider a function f from Rn to 0, 1. And I define a function f tilde from plus minus 1 to the m to 0, 1 by f of x. F tilde of x is f of, well, I'm going to plug in 1 over square root of k, sum of xi, etc., 1 over square root k, sum of xi. And let's see, so the first sum I'm going to take from I equals 1 up to k, and the last one is going to go from I equals something up to m, right? So what I'm doing, right, is I'm dividing my Bernoulli variables into chunks, and I'm taking this sort of binomial for each chunk and normalizing it so it sums to a Gaussian. Okay, and what you'll notice about this function f tilde is that it's 1 over square root k Lipschitz. Right, meaning if I flip a bit of f tilde, sorry, that's not true. I have to assume that my original function is L Lipschitz. Right? If I flip a bit of my function f tilde, then it will change one of these binomials by at most 1 over square root of k, and so it'll change f tilde by at most L over square root of k. And the point is then that if I look at this error term, right, this error term can be bounded by the effect of flipping the I plus 1th bit. Right? So this is even true without expectation. This thing is smaller than L over square root k. Right? And so when I cube it and take expectation, this thing is smaller than L cubed over k to the 3/2. Okay? And so now if I sum this thing up from I equals 1 up to, okay, so I made a problem here, which is that I have an n here and I have an n here. So let me make this a d. Okay, so I sum this up from I equals 1 up to n, and I get here this times n. Okay, and now the point is that k is like n over d, right? So this whole right-hand side is order n to the minus 1/2. Sorry. Yeah, and mixed up my n's and m's and d's, but hopefully it's clear that that when I apply this limit, then the error term vanishes. Okay. And the point is that you really need the third order error term here, right? If you had a second order error term, then nothing would vanish, right? And so you really need this statement is true for j's that satisfy a second order condition. Okay. And okay, so I also claimed that you can get from here to the majority of Stablest theorem. I think, let me not go into that too much. So what you have to do is you have to show that these things can be bounded in terms of the maximum influence, and you use some hypercontractivity and so on. Okay. Okay, so now all of this was actually discussed at the last workshop, but the sort of departing point for today is that I want to point out that actually this proof works in greater generality than what I said before. In particular, it doesn't require IID variables x1 through xn and y1 through yn. So let me state two conditions, and I'm going to claim that the proof works for an arbitrary joint distribution satisfying these conditions. Okay. So the proof of the theorem works provided. So what I did is I applied this induction thing, and I assumed that at every step of the induction I have sort of row correlation. So this is the condition that I needed for the inductive step to work. And then I also applied the base case of the induction every time. And so basically I'm saying that these two Runny correlation hypotheses are essentially all that I needed for the proof to go through. Right? At every step when I do the induction, I need to be able to put a row on the off diagonals of my matrix, which is no longer there. But okay, and this is for all I. So I guess the statement is, if there exists a filtration f tilde, if there exists a filtration f1 through fn, such that this is true, then this statement of the theorem also holds. Okay, so that's all very nice, but doesn't seem very useful, maybe. So what I want to do today is give you a couple examples where we can check this condition. And unfortunately, we don't really know very much about this yet. So I would like to say that there are a lot of interesting examples, but I can only give you a couple right now, and hopefully there'll be more. Okay, so my examples are going to come in two main categories. The first category is when x1 through xn and y1 through yn come from a Markov chain.
It's like a sequence of measures that are like
Sequence of,
sigma algebra.
yeah.
Less and less four, or something like that.
Sorry? A sequence of sigma algebras.
So it's a sequence of just asking for the definition of filtration.
Okay. So the proof works as long as there exists a sequence of sigma algebras which are increasing and have this property. This is what I need. I don't even technically need my functions f and g to be functions of disjoint sets of variables, but I guess in the examples they will be. So I really just need a sequence of sigma algebras. Okay. So my first example to suggest that this is maybe an interesting result is I consider a Markov chain. For now, let's suppose it has finite states. Call the state space S, and call the transition matrix P. Okay. Now, actually, I don't just want one Markov chain. I want two Markov chains. So actually, now I'm going to think of a Markov chain on ordered pairs of the state space. And some transitions p tilde. Okay. And now let me suppose some things about p tilde. So first of all, I'm going to impose a condition that says that the sort of marginal Markov chain I get by just looking at the first coordinate is going to be according to this. And same for the second coordinate. So what does that mean? Right? So for all ik, the sum for j and l of, okay, so p tilde, right, it's a Markov chain on S cross S, so to write its transitions I need two pairs of vertices, right? So I, j, k, l, this thing should be equal to p, I, k, right? And then similarly, if I just fix JL and I sum over IK, right, this is just saying that the marginals of the Markov chains are the right ones. And now I need a condition that's going to tell me that the Markov chains are sort of at each step are have correlation at most row. And well, if you just think about it for a second, then this is what you come up with. For all v of w, the sum of p ij kl vk wl, right? So this is what I'm saying is I'm starting at position ij, and I'm looking at, so I guess this is a function of the next state in one. Right, so V is in.
Are you sure it's the sum about G and L, the first one?
Did I make a mistake? This one?
Yeah, there should be some only over L, no?
Uh,
And if it's for any G.
let's see. So this sum over JL is marginalizing out whatever happens to the second guy. Right? Is it not?
I would say that it's okay for any G, J, the sum over L.
think it should only be a single summation.
So you want me to put a j here?
Yeah.
Some. Just over L.
So that's saying I tell, yeah, right. So I'm telling you where is the,
Yeah, then the first coordinate will be the Markov chain.
okay, maybe. I have to, sorry, it's not the right time for me to think about this, but the condition that I want is for the marginals of the Markov chain to be these marginals. Okay. Right, and the other condition that I want is no matter where I am, the next step that I take is not going to be too correlated between the two chains. Right? And let's hope I didn't make a mistake on this one. So this thing should be smaller than rho times the square root. So I have a sum over k now of and a sum over k now. And this should be true for all v and w, which sort of have mean 0.
Is that for all ij?
Yeah, this is for all ij. Right, so what I'm really saying is I tell you where your two coordinates are right now, and then they're both going to take a step, and those steps are not going to be too dependent on one another. So
Something is still wrong.
So after you corrected it, the way you corrected it is like assuming that they evolved independently. You don't want them to evolve independently. So I think the way you wrote it before was okay.
how about we stick with the way that I said it and not the way that I wrote it, right? They have the right marginals.
Yeah, but here, don't you want the WK or the WK squared?
Squared. Thank you, squared. Right. Right. I want to think of WK and VK as being functions of the position, and then this thing should be the variance, right? And that thing should be the covariance. Okay. What happened to the Okay. So anyway, I claim that when I write these conditions down correctly, then what it implies is are exactly these two things. Okay. So what I'm saying is that for such a Markov chain, I have an inequality for the noise stability, right? It goes like this. Expectation of J f, so this is a function potentially of the whole path. And a function g that's also potentially of the whole path. This is smaller than j of the expectations. Plus plus a third order error term. Okay, let's make this a little bit more interesting with an example.
So, who can derive this without even knowing your proof, just deriving this from your statement by injecting the Markov chain into the definition of f and g? Does that make any sense?
So you mean you want to go from the original majority of Stablest theorem
Right.
to this statement?
From your, I guess, from your proof.
You can, from my proof.
That's what he's doing?
Yeah, that's what I'm doing, essentially.
Well, but you observing that the proof can also apply here. I'm saying I don't even care about the proof.
Just from the statement? You're saying that because the updates are generated independently.
The function could take care of this, assuming it is the space S is rich
Yeah.
enough. You can
Okay, so I think maybe actually you can do this straight from the statement.
You can derive everything.
But I don't think you can get this from the original majority of Stablest theorem, because then you have an error term which is not written like this, which is written
from your proof.
from my thing. Yeah, maybe you're right. So I think my second example, you can't do this, but we'll see. Maybe you can also. Okay, so I guess this is still part of example 1. Let me call it example 1a. See, I'm starting to run out of time. So, okay, so let me take my state space to be the cube. And my Markov chain is going to be, at every time interval, I'm going to choose an index. And I'm going to choose a sign. And then I'm going to choose another index and another sign in the following way. With probability rho, I'm going to set j equals I and tau equals sigma. Otherwise, I'm going to set j, I'm going to choose j and tau independently of I and sigma. And I'm going to set x sub I equals sigma, sorry, x. Right, so this is the Markov chain at time t, and I'm setting its ith coordinate to sigma. And the Markov chain at time t, the jth coordinate will be tau for the other one. Okay? So I claim that these transitions satisfy the conditions. They're not, they have correlation rho. Okay, and the other thing I claim is that actually the stationary distribution of this Markov chain is the rho correlated distribution of the cube. Right? So if you think for a minute, right, if I start with something that's rho correlated, and then I do this, then each coordinate afterwards, well, you know, the coordinate I is going to be rho correlated, and all the other coordinates, well, if they weren't chosen, then they're still independent, right? Well, if they weren't chosen, then they're still from the stationary distribution, which was rho correlated. Right? So let me say this again. Stationary distribution is rho correlated distribution.
Sorry, could you clarify this again? So all the other coordinates remain the same?
All the other coordinates remain the same. I'm just changing one coordinate of each. Okay? And now, okay. So actually, there's a special case of this that I claim is still interesting. Rather than looking at functions of the whole chain up till now, I'm just going to look at functions of the endpoint. And what do I get when I look at functions of the endpoint? Well, when I apply... Okay, so now I have a sum from I equals 1 up to n of an error term. Okay, and now my point is that actually the sum doesn't go from I equals 1 up to n. And the reason is that this Markov chain mixes after a while. And so anything that happens before time n minus a constant times the mixing time doesn't affect the error term, or it affects it an exponentially small amount. Okay? And, okay, so now I'm going to do something. So suppose that f...
Same n in the dimension on the cube and the number of steps in the...
no, I don't.
S is plus minus
M.
1 to the n.
Yeah. So I have a cube of a fixed size, n, and now I'm running a Markov chain on it for a very long time.
Yeah.
But the first bit doesn't affect it, right? Only the last
So
part.
maybe you want to use t or something for the time. Thing.
Uh,
You have two n's, they're not the same.
Thank you. So I have m here and m there. Right, it's the ending time of a Markov chain run for n steps. Okay. Now, if my function is Lipschitz, then this thing, well, the error term is at most L times the mixing time. Okay. So in particular, if L in this example is n to the minus a half, like I was doing before for getting Borel's theorem, well, you can see that the mixing time of this is n log n, and so the error term goes to 0. Okay, so I've...
This is a plus?
Yeah, thanks. Okay. So we haven't gotten very far. It's almost the end, and I've gotten another Borel's theorem again.
You probably want L cubed, otherwise it won't go to 0.
You're right. Sorry. The error term is a cubed, And so I have an L cubed. Right, thanks. Okay, so this was maybe not such an interesting example because it got us something that we knew before, but it sort of serves as a starting point for considering other examples. So let me just sort of quickly say one more example, just in words. Rather than considering the cube, I can consider linear orderings on an alphabet of size n. And there's tons of Markov chains that have been studied for this one, right? So let me do one, which is at time t, I pick a card. So, okay, it's a deck of cards, right? My elements 1 up to n. I pick a card in deck 1. And with probability rho, I take the same card from deck 2. Right? Otherwise, I pick another random card from deck 2, and then I put them both on top. Okay? This gives me some Markov chain. Right? It will. So if I pick the cards uniformly, it will tend to be each Markov chain individually converts to uniform, right? But they're not independent, right? Because they tend to have the same cards on the top, right? And so I claim that if you have a Lipschitz function if you have a Lipschitz function of the stationary distribution in this Markov chain with a small Lipschitz constant, then you also get Gaussian noise stability for this model. Right? And the Lipschitz constant that you have to take is going to be 1 over square root of n, which is sort of large. Well, it's much smaller than the diameter, I guess, of the state space. Right? Yeah.
1 over root n. What is smaller than what?
Well, okay, so the Lipschitz constant that you have to take, so it's quite small, right? It's going to be 1 over square root the number of letters, say, right? Now the diameter of the state space, if I consider the distance where two things are connected, if I can go from one to the other, is order n, right? And so this is a...
1 over root n is less than n, is that?
1 over root n is less than 1 over n, I guess. So what I'm saying is that my function can take... 1 over root n.
1 over 1 over root n is smaller.
1 over 1 over root n is smaller than n. Thank you. Right. So I guess what I'm saying is that my function is very much independent of small changes in the state space, but it nevertheless sees the whole space. Right. It can vary widely over the whole space, but not by adjacent transpositions. So these sort of functions which can't see local things, but are nevertheless non-trivial globally, they satisfy this noise stability. Okay. Very quickly, in words again, the other example that we have, instead of a Markov chain, so it's going to be again a distribution on plus minus 1 to the n, but now instead of independent, I take plus and minus 1 to the n to be distributed according to an easy model on some bounded degree graph with relatively high temperature. And then you can show that if the temperature is not too high, and then I have to tell you what's y, right? What's the noisy version, is I run Glauber dynamics for a short time. Okay, and then you have to check that if the temperature is relatively high, then you don't have much correlation between a vertex at time 0 and a vertex at time t. Okay, and then what you get, so when you check that, is you see that this correlation condition holds. And then the next ingredient to get something non-trivial is to show that you can deal with the error term, and it turns out that some sort of spatial mixing is enough to deal with the error term. So let me not say anything more about that, and go on to some questions. Okay, so I guess what I've tried to get across is that if you have distributions which are not too correlated and depend a lot on many small things, then you get a noise stability theorem for them that says that they're not more noise stable than Gaussians. Okay, but this was only for global functions, right? It's only for functions that do not see small changes, right? So you could ask, and do not see small changes, it was sort of in a very strong sense because I asked for a very small Lipschitz constant. Now in the majority of Stablest theorem, you don't have to ask for a small Lipschitz constant, you can ask for low influence. And so the first question is, what can you say for functions which are not necessarily global in the sense that they're very smooth, but which don't depend too much on any one coordinate. And this is sort of, I'm not even quite clear what the question should be, because the notion of, say, influence of a coordinate in general is, you know, I mean, you can make definitions, but I'm not sure what's quite right. And the second question is maybe a little bit more specific, but not much, which is we can construct examples of Markov chains that satisfy these sort of noise stability bounds, right? But it's sort of one example at a time, right? I mean, I don't, right? So I guess the question here is what sort of joint distributions arise like this, right? So I have a Markov chain, and I evolve it sort of twice in parallel and dependently, right? What sort of stationary distributions can I get from that? Because every stationary distribution that I can get from that sort of a Markov chain satisfies this inequality. So that's all. Thanks.
More questions, comments?
So at least in a situation like easing model, it's clear what is the influence, and I think this, you know, so you choose a variable and you just do one Glauber move on that variable one. So refresh it according to the conditional distribution, and then you have what is the expected. You know,
right.
You can ask what is the change there.
Right. So you're right. Actually, in the case of an easing model, the question is well defined, but I don't know how to answer it. And the reason is, if you look at what you have to check for this correlation condition to hold, then you end up having to condition on basically a bunch of vertices at time 0 and a bunch of vertices at time t. And this is a very non-Markovian thing to condition on. And it makes things a pain. And one thing that it makes to be tricky is when you do the majority of Stablest theorem, and you want to, so we gave this condition in terms of martingale errors. And if you want to apply hypercontractivity to then get influence from that, then you sort of need to use the fact that you can commute a noise operator with the martingale. And that really uses independence. And so I don't know how to do that for the easing model.
It's a question I already asked you, so maybe I ask everybody. You have this definition of strong concavity, which means that you take the Hessian of your function and you put a rho on the cross-diagonal terms. And when rho is 1, this is just the usual definition of non-negativity of the Hessian, and it's equivalent to the concavity of the function, which may characterize through 2 points. So when you have a rho, is there any characterization with 2 is not enough, 4 is not enough, as you showed on the cube, so maybe 8 or 16?
Right. I mean, I should mention, so one thing that Michel pointed out before is that there's at least one more interesting example of a rho concave function, and this is, well, I guess the hypercontractive function, if you think about it. You can prove the hypercontractive inequality just by plugging in a certain function into this general statement, and it turns out to be rho concave. So one other question in addition to that is, are there other interesting examples of rho concave functions?
Oh, sorry, yeah.
Well, often when you have some property for Gaussian, you can go to Poisson. So I was wondering, can you start, or initially, so the first result of Borel, is there an equivalent for Poisson distribution, for example?
No, the thing for Poisson is not true, because it depends too much on one event, I think. So if
you have two Poisson and you have to say that they are correlated.
Right.
So first you have to define what it means. It
Right.
means that I think you have a first Poisson and you let it evolve according to the Markov chain, which has invariance for this Poisson, with an rho will be the exponential in time or something like that. And can you have such property for the such thing like that?
So I'm not sure if this is exactly the same as, but we did consider some sort of Poisson, and what you get is it doesn't matter if your ever term is second order or third order or fourth order, it still contributes. And the reason it contributes is because in Poisson it is controlled by rare events, and so the moments don't decay. So I think it's not true for Poisson, this sort of thing. Might be a different Poisson than the one you're thinking of.
Thanks again.